Welcome back to Doors and Dice. This is the perfect coffee, mathematically correct. This little mini-series is going to try and calculate different things to do with coffee, whether that be temperatures, sizes, or perfect ratios. After asking you guys to spill the tea on which you prefer, most of you seem to prefer hot coffee then iced coffee, tea then iced tea. This video will also be applicable to tea, although all the calculations are done by coffee. My favourite is a hot coffee, 2 sugars and a little bit of milk. I'm going to give you a quick preview of what's to come. First, we're going to be looking at the average coffee and the different ratios of milk and water. Next, we'll be talking about the mug material since that impacts a lot of the heat properties of the coffee. We'll be min-maxing the amount of milk that you can get for the amount of heat that you can get into your coffee, and we'll be talking about reheating your cold coffee if you forget it. The original point of this video was related to problem 4, and we'll actually be discussing that a little bit more in episode 2. Problem 4, however, can be broken down into 3 different parts. Part 1 is reheating your cold coffee. Part 2 is reheating a black coffee, and Part 3 is recooling an iced coffee once it reaches room temperature. Before we start, we've got a few assumptions to state. Temperatures are going to be hot water at 100 degrees, hot and cold milk at 65 or 4 degrees respectively, room temperature at 20 degrees, hot but not burning, max temperature of 65, so this is where you can drink it, it's going to be hot but it's not going to burn you, warm temperature where it's not cold enough to actually be disgusting but still drinkable. Ice is going to be minus 18 degrees, this is the average freezer. 95% is a full cup, this is to avoid spillage. 20% of your cup is going to be milk. The cup shape is going to be approximately a cylinder. And the cup size is going to be 2 by 2 by 4 and the volume of 250. Now 100 degrees is a little bit high, but we'll talk about that more in episode 2. As well as that, in episode 2 we'll be covering more about the cup shape and size, however volume is still going to be important here. Now the assumptions are out of the way, if we ever need them I'll bring them back, so don't worry about remembering them. Problem 1, the average coffee. Volume is going to be 250 milliliters split 20 to 80 milk to water ratio. The volume therefore is 19% milk, 76% water and 5% slosh room. As 19 and 76 are not really the nicest to measure on a cup, I would suggest 20 and 75 as this doesn't change the numbers too much, but it's a lot easier to measure on a human scale. The volume therefore is 50 milk, 187.5 water and 12.5 slosh room. The usable volume is 250 minus the 12.5, and then we can take the ratio of the volume of milk and water to the usable volume to find out how much milk and water is actually in the coffee. Keep in mind that there's an additional 5% slosh room above the coffee, and any of the percentages we give are going to be of the coffee and not of the cup. Any percentages of the cup I think should be coming up in episode 2 as opposed to any episode 1, if not I'll let you know at the time. Now if you've never done physics or chemistry before, specific heat capacity may be new to you. And it's literally just a measure of how much energy you need to put into a material per the gram of material per degree that you want to raise it. It's literally a specific measurement for each material for how much heat you need to put in for it to actually go up. This is a really key concept when it comes to how much heat is in our coffee. Now you know how specific heat capacity works, let's use it. So it's 4.18 for water, and for milk it's about 3.9. Now it depends on the milk, whether it's oat milk, full milk, etc, because it is specific to each material, but it's measured in joules per grams per degree C. Now we're not really going to be measuring things in grams because we're using liquids, and therefore we do need to change it into milliliters. Now for water that's simple since grams to milliliters is exactly 1 to 1. For milk however the density is 1.03, so therefore we need to times the 3.9 by 1.03 to give us 4.02 joules per milliliter per degree C. The coffee K therefore is 21% of the milk's K and 79% of the water's K. So 0.21 times 4.02 plus 0.79 times 4.18. This therefore gives us a coffee K of about 4.15. Now this is extremely close to 4.18 at 99% of that, and therefore we know that the actual amount of contribution of heat contribution from the milk is approximately the same as water in terms of milliliter per milliliter. So the temperature contributions therefore are the milk's K over coffee K and the water K over coffee K, and that gives us 20.4 and 79.6% respectively. Before we finish problem 1, we actually need to look at problem 2 and finish that quickly. The mug's materials play a large role in the way that the heat stays in the mug and as well as transferred to the mug. The most common mug materials are porcelain, paper, polystyrene foam, stainless steel and glass. I'm specifically choosing stainless steel single walled, as of course a double walled with a vacuum in the middle is going to be the best in terms of sheer heat storage. A quick recap on how heat is actually transferred. If you've got a hot molecule in a box and the molecule collides with the side of the wall, the hot molecule is going to give the wall a slight amount of heat and lose some of that heat from the molecule. Conversely, if you've got a colder molecule and it's going to move through the box, then when it slowly moves through and finally collides with the box, it will actually take some of the heat from the box, causing the box to go colder and the molecule to go slightly warmer. This is where specific heat capacity comes into play. So the energy to warm something, or the Q warm, is equal to the mass of the material times the specific heat capacity of the material times the change in temperature. The change in temperature here being the 100 degrees minus the 20 degrees room temperature cup, so therefore 80 degrees. Using the materials, their average specific heat capacities, and gives us the joules. We can then use the equation Q lost to the mug equals the mass of water times the specific heat capacity of water to get the change in temperature of the water by rearranging as so. We can then sub all the numbers in and we can get the degrees C lost to the mug per type of mug from the water. So now we know how much heat is lost from the water straight into the mug as soon as we pour it. However, there's also heat lost per second. Let's look at how heat is lost. So there's conduction, which is solid to solid, convection, which is solid to air, evaporation, which is liquid to gas, which is a state transformation, and radiation, which is literally the material moving and transferring some of that movement energy into light energy. Conduction is actually a really complex thing to calculate. However, it makes up such a small percentage that I'm just going to completely ignore it, and I'm sorry. If you have any suggestions in the comments, please do let me know. I think conduction makes such a small contribution because the cup is concave on the bottom and therefore reduces the amount of actual contact area with the coaster, as well as the coaster generally being heat insulating. So therefore, it doesn't really make up that much difference of the heat loss in the situation, and therefore I'm going to leave it out. So since we're ignoring conduction, let's move straight into convection and Newton's law of cooling. When we've got an air molecule flying through the air and it collides with our mug, it's going to take some of the heat energy from the mug and transfer it into the molecule. When it does this, it lowers the energy in the mug, cooling it, and since heat energy is literally just the movement of molecules, the air molecule will ping off at a higher speed. This can be calculated by Q dot convection equals H convection times the area around the mug times the change in temperature. So H is just a constant, and this gives us 12.8 watts. Watts being joules per second. Now let's talk about radiation and the Stefan-Boltzmann law. It's a little bit more complex, but it's really interesting when we get into it, so just bear with me. Now when these molecules are moving due to the heat energy they've got, they're giving off just a little bit of energy in the IR spectrum. Now the IR spectrum is what we use for infrared cameras, for example, so you can see at night time. This is not the same kind of radiation as a nuclear power plant, but it is radiation and it is interesting. Whenever these molecules are moving, because they've got a small charge in them, say in their nucleus or their electrons, they're giving out this little bit of IR because of that. Because you can't move any sort of charge in the universe without having to give up a little bit of radiation into the universe. This can be calculated by Q dot radiation equals epsilon times sigma times the area of the cup times the temperature of the cup to the power of 4 minus the temperature of environment to the power of 4. We can sub in some numbers and get the emissivity for each of the different material types, and we'll discuss this in a minute. I put a lot of time and effort into researching and making this video, so if you know anyone who loves science or coffee, please share it with them as it really helps me out. Thank you very much. Now let's move on to evaporation, which is just the heat loss from molecules turning from a liquid into a gas and taking some of that heat away with them. Because any gas molecule of the same type of material, say a water molecule and a steam molecule, they're going to have more energy in the gas phase than in a liquid phase, and more energy in a liquid phase than in a solid phase. We'll come into that a little bit later when we talk about ice. So we take the area on top of the mug and we use this equation here, which is M equals HE, which is a constant, times the area on top, times the pressure of a saturated system minus the pressure of a normal air system. Now a saturated system is just air that has got 100% humidity and you cannot get any more molecules of water from the liquid phase into the gas phase. We can sub in some numbers, which gives us 1.05 times 10 to the minus 5 kilograms per second. Q dot evaporation equals M times LV. Subbing in some more numbers, we can get the number of watts that we lose from the mug, 23.8 joules per second. Before we calculate the total heat loss, we need to calculate the heat loss to the spoon as well. The most common spoon types are stainless steel or plastic, and these come in at 20 grams and 5 grams respectively. Using the usual calculation, we can figure out that there's 800 joules into a steel spoon and 600 into a plastic. Transferring this into degrees Celsius, we can see that there's essentially no difference. I'm just going to leave it there. Now this table contains all of the watts from convection, radiation, evaporation, and I've ignored the spoon since it really doesn't add anything, and therefore we can see that evaporation is by far the biggest loss of heat. We can also see that there is only a difference in the radiation per material type, and in total we can see that the steel single wall is going to lose the least amount of temperature per second, followed by the ceramic one. So now that we've finished problem 2, let's move back to problem 1 and the average coffee and summarise what we've got so far. We've got the different properties of milk and water, and we've also got the different materials, how much heat is lost to each of the different materials, as well as how long the material will hold on to the heat over that temperature range. So now that we've calculated the properties for the average coffee, we can start to use these to calculate some other properties about the coffee. For example, we can calculate the temperature of the coffee with cold milk using the proportion of milk times the cold milk temperature of 4 degrees plus the 79.6 times 100 degrees of the hot water. We can also sub in for using hot milk, and this gives us 80.4 degrees and 92.9 degrees respectively. Therefore, the cold milk coffee is 15 degrees above our maximum temperature, and hot milk coffee is 27 degrees above a maximum temperature of 65 degrees. So now that we know the average coffee is going to be well above the starting drinking temperature of the coffee, how long until it's actually drinkable? We can calculate this by using coffee's temperature minus the temperature lost to the mug divided by the cooling rate. Since we have all of this, we can sub in the numbers. For example, the porcelain using cold milk, 15 minus 9.1, divided by the cooling rate gives us 2 minutes and 14 seconds. We can then sub in the rest of the numbers, and that's the results. I think it's better to look at them as a graph. As you can see, a porcelain cup is going to be just over 2 minutes, compared to the paper or polystyrene at over 5 minutes. The stainless steel one is quite close to the polystyrene and paper, but the glass is about middle of the pack. Now interestingly, when you use hot milk instead of cold milk, the results start to bunch up quite a bit. Porcelain, for example, has started to catch up to glass, and glass has started to catch up to the rest. Paper and polystyrene have now actually fell behind stainless steel, and stainless steel is now in front. This is interesting, as it suggests that the initial heat sink into the materials means less when you've got a hotter material. This does make sense as you've got a less percentage overall, but the results are actually quite staggering, as you can see. So now we know how long it's going to take until we can drink it. How long until we can't? You can do this by taking the time in the temperature range and adding that to the cool down time, and this gives us the total cool down time as shown here. This was then graphed. As you can see, the cold milk, the ceramic is at the bottom again, glass is at the second bottom again, but stainless steel with cold milk has now actually came out in front. When you use hot milk, it comes even further in front, and porcelain and glass are catching up again to the paper and polystyrene, although paper and polystyrene are still better. So now we've found how much temperature is going into the mug and leaving the mug, as well as what our average coffee looks like. Let's move on to problem 3 and the maximum possible milk content, because I know that some of you love a lot of milk in your coffee. So let's use porcelain as our example, and we're aiming for our target temperature range to be between the 55 and 65 degrees. So we can use the 65 degrees plus the heat sink into the porcelain. This equals the amount of milk, which is represented by A, times the temperature of milk, which is 4 degrees, plus the temperature of water, 100 degrees, times the amount of water, which is 1 minus A, just everything left over that isn't milk. This gives us 27% milk. If we want to know the minimum temperature, so you've literally made this coffee and it's going to be just drinkable right now, maximum milk content is going to be 37.4% milk. So now that we've calculated it for the cold milk, let's calculate it for the hot milk too. So let's sub in 65 instead of 4. So aiming for the 74.1 degrees, we get 74%. When we add in the 65 degrees milk to get the 64.1 degrees, we get 103%. We get 103% of a full cup. Interesting. So the reason for this is pretty simple. The 65 degrees milk is obviously hotter than the 64.1 degrees that we're aiming for, and therefore the milk is always going to make the cup hotter than our target temperature. Now this is actually a good thing because it means you're never going to be drinking it at the coldest temperature, so you'll actually have some time to actually drink your coffee. Of course, all that was for the porcelain, and now we've got the results for the paper, polystyrene, stainless steel and glass respectively. Now I'm going to move on to the question that inspired most of this video, the cold coffee conundrum. I was gaming a lot and forgetting my coffee, and I was wondering, how can I reheat this so that it still tastes really good? I don't know if you've ever tried it, but just putting hot water into your coffee and even trying to account for the sugar and coffee that you've missed never really tastes that good. Then I realised it's probably because of the milk content being different. Now, I drink my coffee with different levels of milk and I don't really mind, so I didn't think that that would be the problem. I thought I would calculate it out and see if it really was the problem. Now, the reason that I keep forgetting the coffee while gaming is actually really interesting and will be a big part of episode 2. Please stay tuned for that because a lot of work has went into this and I can't wait to release it. So the milk to water ratio should be unchanged in the overall coffee at the end. It will still be 21 to 79 as we calculated earlier, and if you haven't seen that, go back and watch that. We're going to have some cold coffee at the bottom of the cup in a 21 to 79 ratio. We then need to add in some amount of milk and some amount of hot water to heat it back up. This is how we calculate it. So we'll label it as X, Y and Z, milk, hot water and cold coffee respectively. The remaining space will be in a ratio of 21 to 79 milk to water, and therefore we can look at it like this, that 1 minus the cold coffee times the 2 percentages equals milk and the water. Therefore, the temperature that we're aiming for, in this case for a porcelain cup, equals the room temperature cold coffee of 20 degrees times the cold coffee percentage, plus 4 degrees times X, which is the percentage of milk, times 100 degrees times the Y, which is hot water. Keep in mind the following ratios are so that your coffee is perfectly drinkable now and will be drinkable until it gets cold, so it will not be too hot and you'll have the ample amount of time to drink it. So we'll see for 55 degrees cold milk, the different percentages of cold coffee, milk and hot water. 65 with cold milk, 55 with hot milk and 65 with hot milk as well. We can label the percentage of cold coffee so we can see how high up the cold coffee needs to be in the cup, and if it is below that then it will be hot enough, and if it is above that then it will be too cold and it will not be a pleasant drink. So you can see that the porcelain has the lowest one at 10% for the 65 with cold milk. So what I'm saying is if you've got 10% or less cold coffee in your cup, you can just heat it back up, although that seems kind of pointless. The other results, however, are all pretty useful. For example, the porcelain in 55 degrees cold milk, about a quarter of your cup can still be cold coffee and you can reheat it and it'll still be an effective temperature for you to drink it at. When you're aiming for higher temperatures, you obviously need more hot water to heat it back up, so therefore you can have less cold coffee in the cup. And if you're using hot milk, you can use less hot water, therefore allowing you to have more cold coffee, as you can see by the percentages. For completeness sake, I thought I would give you all the percentages so that you can see how it is broken down. However, of course, all of these are in the exact same ratio as each other. Now I promised if you don't have any milk in your coffee that there would be a solution for you too, and here it is. So you've got cold coffee in the bottom of your cup, and you're adding in some hot water to heat it back up. The hot water is therefore going to be 1 minus the cold coffee you've got remaining, and then we can calculate it as seen before. There's just no milk in this calculation. So when we sub all of it in, we get 32% for a warm coffee, and we get 55% for a drink now coffee. You can see the percentages shown in this table. Glass has the best percentage for a no milk, max percentage cold coffee for 55 degrees, i.e. drink it now, and a paper cup has got the best no milk, min percentage cold coffee, drink it over a normal period of time. You can see that porcelain is the worst for this, and paper and polystyrene are the worst for the max percentage one. I'm sorry if you've been feeling left out, but iced coffee drinkers, I've got you too. I might not like iced coffee, but I know most of you seem to. Now, there's a very interesting concept here that needs a little bit of scientific explanation, but don't worry, it's really simple and I'll walk you through it. So why is ice so cold? For example, you put an ice cube into your drink and it chills the entire drink, but it barely melts. Now, one of the reasons for this is that when it melts, bonds are being broken and energy has to go into that. And where does that energy come from? You guessed it, your drink. So while it's taking energy out of your drink to break these bonds actually have quite a lot of energy in them, more than the degrees that it's going to cool if it was just normally taken into account as we've been doing so far. I've got a little animation to show this. So if you've got a hot molecule, aka hot water, and they move past each other, they don't really see each other, they don't really interact, they might bump into each other, but they'll just bounce off like we were seeing earlier. If instead you've got water near freezing, they move much slower, and then they kind of see each other. When they see each other, their bonds can act over the short distance, they're called hydrogen bonds, and they'll pull each other closer and closer together. Now, when there's not enough movement to break these intermolecular bonds, they will actually freeze together, and that is what ice is. Now these are the bonds that we need to break when we melt the ice, which makes it so cold. These bonds are not like a bond in a normal chemical bond. These are actually bonds between the chemicals themselves through space as opposed to through an actual physical bond. These through space bonds are actually really strong, but they only work over a small distance, and that's why the water molecules need to come into contact so slowly so they don't just bounce away from each other before it really has a chance to hold on. Now this is a gross oversimplification, but it gets the point across. As latent heat is given in joules per gram, and we need it in joules per milliliter, we can do a simple conversion using the density of ice compared to the density of water. The density of ice is about 90% that of the density of water, and that's why an iceberg has about 10% of its peak above the water and 90% below. Next time you have a glass with ice in it floating around, check if it's about 10% that's floating above and about 90% that's floating below, and I bet you it's pretty close. The latent heat of ice divided by the specific heat capacity will give us the degrees given from the ice into the water from this melting process. So 306 joules per milliliter divided by 4.18 joules per milliliter degrees C gives us 73.3 degrees C. So what does this mean? For every 1 milliliter of 0 degrees ice, it will cool 1 milliliter of water by 73.3 degrees. However, this is assuming that the ice is at 0 degrees. An average freezer temp is at minus 18 as we made in our assumptions. 1 milliliter of ice cools 1 milliliter of water by the 73.3 degrees plus the 18 degrees, giving us 91.3 degrees. Right? Sadly, it gets so much more complex. For every 1 milliliter of 0 degrees ice, it will cool it by the 73.3 as stated. However, the specific heat capacity is very specific and is specific to ice as well. So we need to use our specific heat capacity equation as shown here, except I made a mistake earlier and called it K instead of C. So I'm very sorry if you've made it this far and have been screaming at the screen. It is meant to be C instead of K. I am very sorry. But we can continue with C here. So Q equals the volume of ice times the density of ice, so that we keep it in volume, times the specific heat capacity as C, times the change in temperature from the ice going to the water. So the energy difference then is 1 milliliter of ice times the density, about 90% as I said, times the specific heat capacity, which is a lot less than water, times the change in temperature. This gives us 34.5 joules per milliliter when you're going from the negative 18 degrees C ice to the 0 degrees C ice. Now of course we need to see how many degrees this changes our water temperature by, so we use our normal calculation here, using C instead of K, and we rearrange to find the change in temperature. So 34.5 divided by 1 milliliter times 4.18, which is the specific heat capacity of the water as we've seen before. This gives us 8.25 degrees C change in temperature. Therefore, when combined with the 73.3 degrees, we get 81.6 degrees total change in temperature. So for every 1 milliliter of 18 degrees ice, we will cool 1 milliliter of water by 81.6 degrees Celsius. We can then divide 1 by the percentage of 0.816 to get us the ratio of 1.227 1 ice to 1.23 water. So that's about 45% ice to 55% water to cool it to about 0 degrees. Okay, so we've nearly got the perfect iced coffee. The overall coffee is going to be an ice to coffee ratio of 45 to 55. Overall, the water to milk ratio is still going to be the 79 to 21 as we calculated earlier. The milk is going to be 21% of the final, so the final is going to be 55% of the initial milk. So we can take 21, the final milk, divided by the 55% of the initial milk to get us 38% initial milk, so that the ratio will stay consistent while the ice is melting. Therefore, the initial water is going to be 62%. For the perfect iced coffee and the perfect ratios, you're looking for a 45 to 55 iced coffee, which is going to be a 45 ice to 38 to 62 milk to water ratio, so that you know how to make your coffee before adding the ice. So you're adding in about 40% milk and 60% water, then adding that to your ice. Your iced coffee total ratio is going to be 45 to 21 to 34. So remember, you're adding in the 17% extra milk. So why would we stop there? We've got one final calculation to do, but before I do it, I want to ask a favour. If you're going to leave a comment, put a unicorn emoji after it, as that's the national animal of Scotland. Then I know that you've made it this far and you're a true viewer. Thank you very much. So you've left your iced coffee and it's got to room temperature. How do we cool it down with just enough ice so that it doesn't water it down, but it's still going to be delicious? So since the ice cools it by 81.6 degrees, it can also be thought of like this. 1 milliliter of ice will cool 4 milliliters of 20 degrees coffee to 0 degrees, approximately. So the ice to room temperature coffee ratio will be about 1 to 4. Therefore, the max room temperature coffee percentage is about 70 to 75%, so you can add just a spot of milk to keep the ratios right. Now let's wrap it up with some conclusions. Problem 1.1, what was the average coffee? Milk and coffee have a very comparable specific heat capacity. Cold milk coffee and hot milk coffee have plus 15 and plus 27 degrees respectively compared to the starting drinking temperature. Problem 1.2, the cool down time. The time was very temperature dependent as well as material dependent, but the best was steel with hot milk and the worst was porcelain with cold milk. Problem 1.3, the total cool down time. The order was stainless steel, then all the others, and then dead last was porcelain. So for problem 2.1, the heatsink into the mug, the worst mug was ceramic, followed by glass, followed by stainless steel, and then well at the front of the pack was paper and polystyrene. The heat loss to the surroundings, the conduction and the spoon were essentially negligible, evaporation was by far the highest, stainless steel had the lowest energy loss per time. Problem 2.3, the drinking temperature range. Stainless steel was well above the others and the others were relatively comparable. Now let's move on to problem 3, maximising cold milk. Polystyrene and paper were in first, followed by steel, glass, then porcelain. For maximising hot milk, it was the exact same order. Let's finish up with problem 4.1, cold coffee conundrum. The paper and polystyrene were better than the steel, which were better than the glass and better than porcelain. For 4.2, the situation with cold black coffee, the max cold coffee percentage was best with glass, then steel, then porcelain, then paper. For the minimum cold coffee percentage, paper and polystyrene were better than glass, which were better than steel, and they were well better than porcelain. For the iced coffee situation, we found out that specific heat capacity is actually C and not K. I'm very sorry about that. The ice is really cold. There's about a 17% extra milk to keep your ratios correct. About a 1 to 4 ratio of ice to room temperature coffee to bring it back down to 0 degrees, and that you can have a max of about 70 to 75% room temperature coffee, so you can add just a spot more milk and still cool it down to 0 degrees. If you're still here, I hope you've learned something, and let me know in the comments if any of this worked in a practical setting. Also let me know if you've noticed any mistakes along the way. Thank you very much for watching, have a wonderful day, bye bye.